Hi, and welcome to this brief concept bite about how the entropy of a process varies with changing temperature. Just like with enthalpy, this allows us to model the behaviour of chemical processes at temperatures other than 25 degrees C, the temperature in which data tables give us values for standard entropy. As I've mentioned previously, the heat capacity of a material changes with temperature, and heat capacity and entropy are intrinsically linked. In fact, the absolute entropy is the area under a plot of Cp over T against T from absolute zero to the temperature of interest. And since entropy is a state function, the entropy of the temperature change is this area between our two temperatures of interest. If we go back to our definition of entropy as being delta S is equal to Q rev over T, it is possible to derive an equation to show how entropy depends upon temperature. Delta S is equal to the heat capacity multiplied by the log of Tf over Ti. As with all derivations, it is out with the scope of this course, but it assumes that the heat capacity is constant over the temperature range studies. This equation is true for both entropy changes at constant pressure and constant volume using the appropriate heat capacity. As should be expected, the bigger the value of heat capacity, the bigger the entropy change for a given ratio of initial and final temperatures, and therefore entropy changes at constant pressure are always bigger than their equivalent at constant volume. Consequently, we can work out the entropy change of any process at a different temperature so long as the heat capacity is constant between the two temperatures of interest. This equation is the parallel of the Kirchhoff equation for enthalpy, but here we can work out the entropy change at both constant volume or constant pressure so long as we use our appropriate heat capacity. Unlike with enthalpy, we can relatively easily determine absolute molar entropies for species, and it is these absolute entropies which are used when we determine entropies of reactants using the fact that entropy, like enthalpy, is a state function. As with enthalpy, being able to adjust the entropy for different temperatures is an important tool in thermodynamics, as most of our processes do not occur at room temperature. We know from the second law of thermodynamics that entropy is fundamental to understanding why chemical reactions happen, and now we can start to understand these processes at different temperatures. As always, I hope this short video has been interesting. If you have any questions, please do not hesitate to ask.